You're watching a Channel 98 NBISD TV production.
Hello out there in TV land. Welcome to another fantastic, great episode of Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. Today is Lesson 30, already to the big 3-0. Can you believe it? Today is also the final chapter, or the final segment, in our three-part series on conic sections. We first talked about the circle. We talked about the ellipse. We've previously talked about the parabola. Today, there's only one left. It's the hyperbola. So say hi, hyperbola. All right, the jokes only get worse as the show gets on. Anyway, the hyperbola is very important. It's probably the least known of all the conics. Many people think that there's no applications, but you'd be wrong to assume that. The hyperbola has many diverse applications, from a path of a comet. It has reflective properties as well that make it nice reflectors in telescopes. And you'll see at the end of the show that there's actually a navigation system that rivals GPS, that actually predates GPS, that is used with hyperbolas. All right, so you don't want to miss that. Stick around, download those worksheets from the district website, www.newbraunfels.txed.net. Grab a pointy pencil and stick around me for about a little bit less than 30 minutes now, and let's learn about hyperbolas. All right, here we go, the big 3-0, Lesson 30, hyperbolas. Okay. Now remember, everything we've been talking about in the last two episodes, and including today, is a conic section. That means it is a cross section of a cone. Okay. In this case, for a hyperbola, we actually have to take a double napped cone, which is a cone with another cone inverted on top of it. If we slice then that cone perpendicular at a right angle to the base all the way through, we get something that resembles this. Okay. So here's our plane that's slicing. And if we do that, the cross section is going to form two branches of what look to be kind of like parabolas. So it's very parabolesque. But we get one branch up here and the other one down here. Now the hyperbolas, when they were first studied in ancient times, were only studied for their primary branch, one or the other. But it was, remember, Apollonius, who not only gave the conics their names, he was the first one in this case to actually study both branches of the hyperbola. Okay, so there's the cone perpendicular to the base. We get two branches right there. Okay, so now you know what it is. Let's look at the locus definition of a hyperbola. Remember, every conic section has a locus definition that starts off with the set of all points. And a hyperbola is going to be very similar to the definition of an ellipse, okay? But it's subtly different, and you really need to understand why it's different, where the difference is. You'll see that's kind of funny in here in just a second. Here it is. A hyperbola is the set of all points whose difference of the distance from two fixed points is a constant. Those fixed points are called the foci, just like they were in the ellipse. Remember, the ellipse was the sum of the two distances, and for the hyperbola, it's the difference. When you subtract the two distances, is a constant. And it's equal to the same constant, which happens to be 2 times a. You don't need to know that for now. But anyway, the difference is the difference. We're subtracting for a hyperbola. Now, if you look at this right here, you've got a foci here and a foci here. So here's one branch of the hyperbola. Here's the other branch. This is one focus. This is the other focus. So from any point on either branch, if you draw a line to the two foci, then call one D1 and D2. When you subtract those two and make it positive, doesn't matter if it's big minus small or small minus big, we can say the absolute value of the difference of the two distances is a constant. Okay? For an ellipse, you added them together. Pretty cool, right? Now what you can think about is a hyperbola is an ellipse that has hyperextended itself. Okay? The foci have moved outside, so instead of opening inward on our foci, our hyperbola now opens outward on there. And there's actually a term in English that is the same as the Greek word for hyperbola, which is hyperbole with an E at the end, and that's a literary device which means excess or exaggeration. And so that's what a hyperbola is. It's an ellipse whose foci have exaggerated or gone beyond the ellipse, and it's hyperextended itself outward. Okay? So a hyperbola can look either like that, where it opens side to side, crossing the x-axis, or you'll see one that could open vertically that would cross the y-axis. Now, of course, we can rotate these through any angle, but we're going to limit our study primarily to the ones that open sideways and the ones that open vertically. Okay. All right, here's another picture side by side of the two different types of hyperbolas we're going to be looking at. The one that opens side to side and the one that opens up to down. Now, notice I drew some lines in on here. These lines are not really part of the graph. We've seen them on other functions. These are actually slant asymptotes. We've seen horizontal asymptotes for rational functions, vertical asymptotes for rational functions, and other functions. Now we have slant or oblique asymptotes. And again, they're just imaginary lines, but notice that they help define the shape of this graph. And I'll show you how to sketch those in and how to even write their equations in just a little bit. Now, let's kind of look at the anatomy of a hyperbola. As with any conic, there's a lot of names, there's a lot of symbols that we have to memorize. And we'll focus our study on the one that opens left to right. But we can generalize that then to the one that opens vertically. So the standard form of an equation of a hyperbola that opens left to right is going to be of this form here. X minus h squared, that's the same as the ellipse. H is the x-coordinate of the center, over a squared. But now notice we have a minus sign right here. Minus y minus k squared over b squared. K is the y-coordinate of the center, and notice it's still equal to 1. If I had simply changed that plus or that minus sign to a plus sign, that would be the standard equation from ellipse from last week's show. So again, the difference is the difference. A hyperbola is always subtracting. Now you're going to see that the placement of the negative, whether it's in front of the y or in front of the x term, is going to have a big difference as to whether a hyperbola is open horizontally, crossing the x-axis, or vertically opening or crossing the y-axis. Okay, so here we go. Assuming that we're crossing the x-axis, here's the types of things we can talk about. The axis that we actually cross, and for a horizontal we cross the x-axis, that's called the transverse axis. Okay? Transverse means to cross. That's pretty easy. We called that axis the major axis for an ellipse, but now we call it the transverse axis. And just like any good parabola, we also have vertices. Okay? This would be a vertex, this would be a vertex, and they lie on the transverse axis. Also on the transverse axis, which is analogous to the major axis, are the focuses, or the foci. We have them inside the curve over here at C0, so C would be the distance from the center, which is here to the focus. And we have the other focus at negative C0, so we still have a focal length, and we call it C. The vertex is A units away, so that would be at the point A0. So A is still the distance from the center to a vertex. C is still the distance from the center to a focus. All right? Now, the other axis that the hyperbola does not cross is analogous to the minor axis from the ellipse. But we don't call it the minor axis. We call it the conjugate axis, the other one, the conjugate axis. And these points right here are essentially co-vertices like they were on the ellipse, but notice they're really not part of the graph itself. But they do help us in defining the shape. And again, I'll show you how to do that in just a second. And of course, those are B units away, just like before. Up B and down B from our center. In this case, it's at 0, 0. And then we have our slant or oblique asymptotes. Got to memorize this information. Similar to an ellipse, different names. Transverse instead of major, conjugate instead of minor. So what does the other equation look like for an ellipse that opens vertically? Okay, well, it's right here. It's y minus k squared over a squared minus x minus h squared over b squared. So notice that the only real difference between the equations is which term is actually negative. If it opened horizontally and crossed the x-axis, the x term was positive and the y term was negative. For the one that opens vertically, the y term is positive and the x term is negative. So that's your key piece of information you want to link to the equation to the graph. The transverse axis, or the hyperbola, will always cross the term in the equation that is positive. If x is positive, it crosses the x-axis. If y is positive, it crosses the y-axis, opens vertically. The center is still at hk, okay? So we still associate the x-coordinate of the center with x and the y-coordinate of the center with k. The only difference within a hyperbola also with the a squared and b squared is, notice I wrote the a squared underneath the positive term each time, and I didn't keep them associated with the x and y. And that's because for an ellipse, a squared was always bigger than b squared, always. It was associated with the major axis. But we can actually have a conjugate axis that's not as large as the transverse. So for a hyperbola, A is always associated with the vertices, which is always on the transverse axis, which is the positive term. You got it? So A is always under the positive term, or A squared is, and B squared is always under the negative term for hyperbolas. Got it? All right. Now, one last thing before we get to work with these guys. Remember the special relationship that related A and B to C, the focal length. For an ellipse, when we were adding in the standard equation, we had to subtract in the c squared equation. It was c squared equals a squared minus b squared. But for a hyperbola, because we're subtracting in the equation, we have to add in the c squared equation. It's the opposite. So in this case, c squared, the focal length squared, is equal to a squared plus b squared. We add them together. This is really just the Pythagorean theorem. Okay? That's very important. You've got to memorize it. Okay, let's try looking at an example now. What do we want to do? We want to sketch that graph right there. Okay, so let's take a look at this equation. Oops, forgot the square. Now it looks better. I've got an x minus 3 squared minus y plus 1 squared. So it is a hyperbola. Squared term minus another squared term. Ellipse is plus. Because the x term is positive, I know the transverse axis is horizontal. It's going to cross the x-axis. Where's my center? Let's figure that out first. The center is at hk, which is going to be at 3, negative 1. And you always want to start with your center, just like we did with an ellipse. So here we go. I'm going to sketch a little coordinate plane. 1, 2, 3, down 1. There's my center. Now, you don't even have to know in the beginning which is the transverse, which is the conjugate. Underneath the x, we have 25. So the square root of 25 is 5. And because it's under the x, that's our horizontal radius, essentially. So I want to go 5 units to the left and right of here. So I'll count. 1, 2, 3, 4, 5. Put a dot. 1, 2, 3, 4, 5. Put a dot. That gives me 2 points. Do the same thing for the y. Under the y is 49, the square root of which is 7. Because it's under the y, that's your vertical radius. So you can go 7 units up and down from the center. Count. 1, 2, 3, 4, 5, 6, 7. And down. 1, 2, 3, 4, 5, 6, 7. Puts me down here. Now, if that was an ellipse, we would connect the dots with a nice smooth circle. But because it's a hyperbola, what we do instead is we make a temporary rectangle or a box that passes through these points. Okay? And it doesn't have to be anything fancy. But if you draw it in there as a dotted line, it's not going to be part of the graph. Now what we can do is we can sketch in our asymptotes. They're imaginary. And what the asymptotes do is they basically define the aperture or the shape of the 2 branches. And the way you draw those is you just connect the diagonals of your box going through the center. And I'm going to do it as a dotted line. So here we go. Dot, 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 dot. What comes next? Yep, dot, dot. Okay? And then I do it the other way, coming down, dot, 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 dot. There we go. Now we have everything kind of laid out, ready to draw our hyperbola. We can draw it over here, or we can draw it up here. So now is where you have to remember, the x term was positive. This one opens horizontally. It's going to open like this across the x-axis. So now here's what we do. We come from this asymptote, and we start curving right down here to that vertex. We have to hit that point, and then we curve back out, approaching the other asymptote. It'll never touch them. But as we go out to the right in this case, we're going to get closer and closer to that. And over here we do the same thing. We come from the asymptote, and we draw it carefully down, touching the vertex, and then curving back out. And we get a hyperbola that looks like that. Now, what we want to do with this example is go ahead and find where the foci are and get the equations of the slant asymptotes. So how do we find the foci? Well, they're going to be on the horizontal or transverse axis, so we have to use this little equation. C squared is a squared plus b squared. So here we go. C squared, the focal length squared, is a squared. Well, a squared, remember, is in this case is not the bigger of the two. It's associated with the positive term. So that's 25 plus 49. Now, really, if you get those confused at this point, it's okay because you're adding them. But remember, a is always associated with the positive term. And so if we solve that, we get c squared is equal to, this is going to be 74. And so c is approximately 8.6 units. And that's going to be the distance from the center along the transverse axis. So if I go 8 units from here, it should take me past my vertex. And it does. It takes me right in there. And then 8 units this way takes me right in there. Okay, so there's the 2 foci. Now what can we do? Well, let's get the equations of the slant asymptotes. The slant asymptotes will always pass through the center of the hyperbola. That's important because to write an equation of a line, you need a point and you need a slope. So the point that we're going to use is the center, 3, -1. Now here's how we find the slope. The slope is rise over run, change in y over change in x. It'll either be positive b over a, or positive a over b, or negative b over a, or negative a over b. It's always going to be the ratio of a to b in some fashion. How do you know which one? Well, remember, rise is y's and x is run. Rise is up, run is horizontal. So all you have to do is look at your y. What's underneath it? 49. So the square root of that was 7. So our slope is going to be plus or minus the square root of the number under the y, which is 7, over the square root of the number under the x, which is 5. You no longer have to remember a and b or b over a. It's under y, it's the y over the x, rise over run. So 7 over 5. Got it? Now that we have that, we can use the point slope formula, which says y minus y sub 1 equals m times x minus x sub 1. That's a real easy equation to plug into, and I'll just carefully plug in now. It's y minus my y coordinate, which is -1, so that becomes +1, equals, now I can get both lines in one equation if I just put plus or minus 7/5 times x minus the x coordinate of the center, which is 3. Now right there, if you leave that single equation, that's not in slope-intercept form. If your teacher wants them in slope-intercept form, you're going to have to distribute and solve for y, and you're going to have to do it twice, once with the positive slope, once with the negative slope. But that essentially right there is both equations of the slant asymptote. Okay? So practice a few of those. You'll get pretty good at them because it's a very systematic process. Whew! Know about you, but I'm ready for a break. Let's take a quick one, watch these public service announcements, and think about this while you're gone. Why did Beethoven get rid of his chickens? The answer when you get back.
The odds of a child becoming a professional golfer? 1 in 140,000. The odds of a child being diagnosed with autism? 1 in 150. You know the odds of autism. Now learn the signs. Go to autismspeaks.org.
Yesterday, my friends told me to smoke some pot, and I did. Then today, they said I should try and fit my fist into my mouth. It fits, but I can't get it out. I'm an idiot. I'm under the influence of others, and that ain't me. That's what he said.
Live above the influence. Above them, above weed.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking to you today about hyperbolas, Lesson 30. Did you think about why Beethoven ended up getting rid of all of his chickens? It's because they kept saying, bok, 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 bok to the mouth. Aside from being able to graph parabolas, 3, 2, 1. Aside from being able to graph hyperbolas given the equation, another thing you might be able to do is write the equation from just pieces of information, if not the graph itself. So let's look at one of those examples. We want to find the equation of a hyperbola that has a center at the point 1, 1, a vertex at 3, 1, and a focus at 5, 1. Well, how are we going to do that? Remember, the standard form is x minus h for one that opens horizontally, x minus h squared over a squared minus y minus k squared over b squared equals 1. But how do we know right away that that one opens horizontally or vertically? Well, we're going to figure that out because we're going to plot the information, and the information on the graph will tell us. But at the very least, we're going to need an A, we're going to need a B, and we need that HK center. That's it, and we need to know which way it opens. Well, they gave me the center, so I already know my H, I already know my K. I'm going to use the rest of the information. They gave me a vertex so I can find A. Once I know what the focus is, and I know what A is, I basically know my C and my A, and I can use that to find B. So there's our map. Now, what I would recommend if you're given information is to go ahead and plot it. I have a center at the point 1, 1, so that puts me right there. I have a vertex at 3, 1. 1, 2, 3, 1. If that, in fact, is a vertex, and this is my center, do we know already which way the hyperbola opens? Left to right or up and down? Yep, it has to open sideways, horizontally. It has to, because a vertex lies on the curve. Otherwise, it'd be a covertice. Okay, so since this is a horizontal distance from the center, I know it has to look something like that. All right? So what do I know then? I know essentially that the distance from my center, 1, 1, to the point 3, 1, which is 2 units, is A. So I also know that A is 2. All righty. I also know the focus is at 5, 1. So let me graph that. 1, 2, 3, 4, 5. There it is. That's the focus. And notice it's also on the horizontal axis. So that confirms that it opens horizontally. The transverse axis is horizontal. Well, remember, the distance from the center to the focus is my C value. And that's the distance from 1 to 5, which is 4 units. So I know C is 4. So I am going to get to use this equation right here. Had it open vertically, I would switch the y minus k and the x minus h. So really, I'm almost to the point where I can just drop it in. I just need to find my b, or my b squared. So remember, c squared is a squared plus b squared. Plug in what I know carefully. 4 squared is 2 squared plus b squared. And if I solve that, I get b squared is 16 minus 4. So b squared is 12. Now we could solve for b. It's the square root of 12, or 2 square root of 3. But remember, what I really want in the equation is b squared. So let's just leave it as 12. Now all we have to do is drop the pieces into the puzzle, and we get the following. X minus h, which was 1, squared, all over a squared. Well, if a is 2, a squared is 2 squared, or 4, minus, the y term is minus, y minus k, well, k is also 1, squared, all over b squared, which we just found to be 12, and then it's equal to 1. So this right here is the equation of the hyperbola, and we really didn't even need to sketch the entire graph to get it. But from there, we could complete the graph, we could finish it, and we could find the equations of the slant asymptotes and all that good stuff like we did on the previous example. But I think the key in this case is to plot the pieces of information that you're given and actually count on the graph and figure out what your A, B, and C are. You'll always be able to find 2 of those 3 from the pieces of information. And then you use the equation, this one right here, to find the missing third one. Okay? Not so bad. Now it's time for Deja Review. Have you ever been wandering around somewhere, been kind of lost, didn't know where you were? Well, if you're lucky, you have a compass, you have a map, and you can read the sun, and you can find your way out. But you know, with this new technological world growing every day, that there are mechanical devices and there's technologies actually that can find our way for us. Okay, GPS, the Global Positioning System, is one such method. But another one that's been around a little bit longer, since 1940, established by the U.S. government, is something called LORAN. LORAN is an acronym that stands for Long Range Navigation. And it's similar to GPS, and it's still used primarily by the U.S. Coast Guard and many other nautical applications or nautical industries use the LORAN. They prefer it to the GPS. Now, the whole LORAN long-range navigation system is built around the whole fundamental idea of a hyperbola and the reflective properties as sound reflects off hyperbolas. And what it does is it kind of triangulates. You basically have a main or a master station that is emitting a sound, and then you have 2 slave or auxiliary stations that are also part of the triangulation. And what you do then is you actually send out a frequency from each of those 3 stations to a boat that is capable of receiving that frequency out on the ocean. And just by calculating the differences in the times, which can be translated into distances, from those 3 fixed known receiving stations, you can actually pinpoint where the boat is at any given time. Remember, the definition of a hyperbola is that the difference of the distances is always a constant. So that's a pretty cool application of math at work in the real world. I'm not going to get into a specific problem because we don't have the time, but you should check out LORAN and check it out and try and maybe do a couple of problems with it. Let me show you kind of how it works, though. Here we have a nice blue ocean, right? And we basically have a master station right here that's at the focus of one hyperbola, And then we have these two auxiliary or slave stations right here that are at the focus of another hyperbola. If this ship is out in sea, we can always triangulate. Each of these send a signal. Okay, this sends a radio signal that's picked up by the ship. This one sends out a radio signal. This one sends out a radio signal. And by calculating the difference of the distances from those three, we actually get two hyperbolas, okay, depending on where the ship is. If the ship is right here, and this is a focus, we get this hyperbola and this hyperbola, okay? And the computers can generate an equation for that very quickly. And then using the slave station and the other master station, we can get this hyperbola right here. Now, because the ship is used, that's common between the two, we basically have the equation of two hyperbolas. And if we find where the equation of the two hyperbolas intersect, which we can mathematically, we know the precise location of the ship at sea that is no longer lost because of Loran, which is built around hyperbolas. Thank you, Apollonius. And thus concludes another great, fantastic episode of Deja Vu, It's Algebra 2, all about hyperbolas. Now remember this about hyperbolas. You're never lost at sea when you've got math with you. That's right. Until next time, I'm Kevin Corpy reminding you to do your homework.